Okay, we're going to look at this example problem where we're relating kinetic energy to work. So one of your first homework problems, there was a student who was holding a book out a window, and then she dropped the book and it fell a distance of 3 meters. So you imagine leaning out the window, holding a book steady out that window, and then just releasing it or letting it go. So the first question is, how much work is done by gravity? So that's really important that we're looking at work done by gravity. And this is, I think we already answered this question in our very first class looking at work and energy. For A, work equals, we'll say F cosine theta times displacement. In this case, since we're dropping straight down, theta is 0 and cosine of 0 is 1. So we can just use the equation F, work equals F times displacement. Okay. Now, here we're being specifically asked what is the work done by gravity. So work done by gravity only involves the force of gravity, and Fg equals mg. So I'm going to use this equation. I'm replacing Fg with the formula for gravitational force. And so we can plug in all of our variables. So our mass is 1.5 kilograms. G is 9.8 newtons per kilogram. And our displacement is 3 meters. And we end up getting 44.1 joules of work. Okay, so ignoring air resistance, how much kinetic energy does the book have when it hits the ground? Now we were just saying work is equal to a change in kinetic energy. And that's equal to our final kinetic energy minus our initial kinetic energy. So in this case, our initial kinetic energy is going to be 0. Because if our kinetic energy is 1/2 mv squared, and if we're holding the book still over the ground, then v equals 0. And if v is 0, then this whole equation is equal to 0. So our initial kinetic energy is 0. So we can write this as work equals EKF minus 0 joules. So work is essentially equal to our final kinetic energy. We just calculated work. If we're ignoring air resistance, the only force acting on the book is gravitational force. So that means that our kinetic energy is going to be 44.1 joules. So that's going to be our answer. Now I want to show you something. I'm gonna erase all this. Okay, so we had just calculated that our work is equal to our final kinetic energy, which is equal to 44.1 joules. But I want to show you something. So if I do EK, our kinetic energy is 1/2 mv squared. We have some of this information. So let's just say we don't know what our kinetic energy is. If we're plugging everything in, we know the mass of the object is 1.5 kilograms, but we don't know what the velocity of the book is going to be when it hits the ground. but we can figure that out. So we would need to find the velocity of the book when it hits the ground. And we can do that a couple of different ways. The quickest way is to use this equation, which is on your equation sheet. It's one of on your front page. It's one of the first things that we looked at. We didn't use it a ton in our first unit, but it's really useful here. Now, if you recall, my initial velocity, if the girl is just holding the book steady outside the window, is 0 meters per second. So that means I can write this equation as v squared equals 2a delta x, because this portion right here is equal to 0. And so if I want to solve for the velocity, I can rewrite this as velocity equals the square root of 2a delta x, because I'm just taking the square root of both sides here. We have all of those components, so we can actually calculate the velocity. So v equals the square root of 2 times 9.81 times 3 meters. And if you calculate that, you end up getting 7.67 meters per second. So we can take this velocity and we can plug it in to this equation up here. So I'm going to do that. And say 7.67 meters per second. And don't forget, you have to square this. So I'm going to calculate this. So it's 1/2 times 1.5 times 7.67 squared. So we'll do 1/2 times 1.5 times 7.67 squared, and we get 44.1. If we come back over here, we get the same answer as when we reasoned through it a different way, that the kinetic energy is 44.1 joules. So all of the things that we learned in mechanics relate to these equations. I think that's really cool. Okay, here's another example. So we have a shuffleboard player pushing a puck. The puck is initially at rest, so that's important. So what that tells me is that my initial velocity is 0, and that's also my initial kinetic energy. We have a 6 Newton force. It's applied for a distance of 0.5 meters. And so what we're being asked is, what is the kinetic energy of the puck and the velocity of the puck? Okay, so for A, we know the puck starts at rest. So like I said, initial velocity is 0. So my initial kinetic energy is 0. We also know that work is change in kinetic energy, which is our final kinetic energy minus our initial kinetic energy. And since our initial kinetic energy is 0, work is going to just be equal to our final kinetic energy. Now, we can assume that Well, when we're calculating work, we know that that's F cosine theta times displacement. And we know that theta is 0 because basically if they're not telling you anything about being pushed at an angle, you can assume that you're being pushed parallel to the line of motion. So that means cosine of theta is 1, and we can write work as work equals F times delta x. We know that the force is 6 newtons. And we know that the distance is half a meter. So the work is 3 joules. Six times 1/2 is 3. Now I'm being asked, what is the kinetic energy of the puck? Well, we already reasoned through this. We said the work is equal to our kinetic energy. So our kinetic energy is 3 joules. I'm also being asked, what is the velocity of the puck? Well, I know that my kinetic energy is 3 joules, so we'll go down a little bit. And I know that kinetic energy is 1/2 mv squared. So I can plug in 3 for my kinetic energy. And I was given the mass of the puck. If you come back up here, the puck has a mass of 0.25 kilograms. So now we're just missing this one variable, and so we can just algebraically solve for it. So 1/2 times 0.25 is 0.125. If we divide by 0.125 on both sides, we get v squared equals 24. And I take the square root of both sides, I get my velocity is 4.9 meters per second. So once we know the kinetic energy, we were given the mass, so we can just algebraically solve for the velocity. Okay, the second part asks, how much work is required to bring the puck to a rest? So the puck is moving, and now I want to bring it to a rest. So what this is telling me, if I'm bringing it to a rest, is that my final velocity is going to be 0. So that means my final kinetic energy is going to be 0. So we're kind of flipping our orientation in terms of what's final and what's initial. So the puck is moving, and it has a kinetic energy of 3 joules, and it's going to come to a stop and have 0 joules. So if we're asking how much work is required, I'll do this down here. So this is B. Work is equal to our change in kinetic energy. So now I know EKF is 0 joules, and my initial, if we start moving, is 3. So the work required to bring it to a stop is -3 joules. So this essentially says that 3 joules of energy need to be removed, 3 joules of kinetic energy need to be removed in order to bring the puck to a stop.